Section: Introduction. In this section, we have encountered various advanced language models, LLMs, like GPT-4, Command-R, Claude 3, and Gemini Pro 1.5, which have been extended to handle longer contexts. Despite their impressive abilities, LLMs still struggle with processing long context inputs efficiently due to challenges with attention calculation and memory demands. One key issue is the linear increase in decoding speed per step as input length grows, mainly because of the computation for attention across past key value pairs, KVs. The large KV cache created during prompting also requires significant memory, limiting model scalability. To address these challenges, different perspectives have been proposed, including strategies like KV cache eviction during token generation. However, many of these methods lack a thorough evaluation of the generated context in long context scenarios. They often focus on optimizing the KV cache during generation steps but overlook compressing the KV cache for input sequences, which is crucial for memory efficiency. In our research, we have identified important patterns in attention features during generation and conducted experiments across various inputs to validate our findings. Based on our observations, we have developed a new method called SnapKV, which efficiently compresses the KV cache for long sequence inputs without compromising model accuracy. SnapKV intelligently identifies crucial KVs with minimal modifications and can be easily integrated into popular deep learning frameworks. We have evaluated SnapKV across different LLMs and long sequence datasets, demonstrating its accuracy and efficiency improvements compared to existing methods. Additionally, we have shown its memory efficiency through tests like the needle in a haystack test and highlighted decoding speed enhancements with varied batch sizes and input lengths. Integrating SnapKV with a leading RAG model has further showcased its enhanced performance capabilities and compatibility with other acceleration strategies like parallel decoding. Previous works have also addressed KV cache compression using various algorithms, such as evicting the KV cache or compressing it for generation steps. However, these methods often overlook compressing the input sequence KV cache, which is essential for reducing memory and computational overhead. While existing techniques may reduce the KV cache size during generation, they do not fully tackle the challenges posed by complex input contexts, leaving critical issues unresolved. Section Summary. In this section, we explore the challenges faced by large language models, LLMs, in efficiently processing long context inputs due to the obstacles posed by KV caches in attention calculation. We introduce SnapKV, an innovative method that effectively compresses the KV cache for long sequence inputs without compromising model accuracy, validated through experiments across diverse inputs. SnapKV demonstrates improved memory efficiency and decoding speed enhancements, showcasing its compatibility with various LLMs and its potential for integration with other acceleration strategies like parallel decoding. Section: Observations. In this section, we will discuss our observations on the patterns in the query key matrix during token generation. We have analyzed various generation contexts and the behavior of attention mechanisms in LLMs. Our findings can potentially be used for KV cache compression and are summarized into 3 key observations. 1. We noticed a consistent pattern across different contexts where specific keys in the prompt consistently have higher attention weights. These active keys follow stable patterns related to the prompt structure and content. 2. In tasks like summarization and question answering, the position of questions within the prompt, beginning or end, does not significantly affect the attention patterns. This suggests that relevant features can be easily attended to regardless of question position. 3. The attention patterns we observed are highly dependent on the context, showing a strong association with user instructions. A context-aware KV compression approach could improve performance. To organize our experimental analysis, we introduce the following terms: prompt length, L_text, prompt, total length of user input. Prefix length, L_text, prefix, length of input before the observation window. Observation window. L_text, OBS. Last segment of the prompt crucial for analyzing different contexts' influence on attention patterns. We define voting as the process of calculating attention weights for each query within the observation window across all heads to highlight significant prefix positions. The hit rate, H, measures the effectiveness of the voting mechanism in identifying essential attention features for the generation outcome. In our study on multi-turn conversations, we found that important keys identified in the observation window maintained their significance throughout token generation. This was validated using samples from the UltraChat dataset. In our analysis of long document QA, we observed consistency in important keys identified through voting in observation windows throughout the generation process across various datasets like QM-SUM, OpenReview, and SPACE. Section Summary. In this section, we observed consistent patterns in the query key matrix during token generation, indicating specific keys consistently receive higher attention weights across various contexts. These active keys seem to be related to the prompt structure and content, showing stability regardless of question positioning. Our analysis suggests that context-aware KV cache compression could enhance performance by leveraging these attention patterns effectively. Section. Effectiveness of instruction positions. In this section, we explore the impact of instruction positioning on the interpretability of LLMs and the selection of important features. We measured the average hit rate for responses using a 32-token observation window and found that regardless of whether instructions were placed before or after additional context, the hit rates remained consistently high across all datasets. This suggests that the patterns identified by observation windows are not influenced by the position of the questions. Moreover, we investigated how different instructions on the same document affect the selection of important features. By comparing the hit rates of important features selected by various instruction response pairs within the same document, we observed that different instructions prioritize different features. This variability challenges static compression methods that rely on fixed policies, highlighting the need for context-aware compression strategies. To address the issue of exponential time complexity in long-context LLMs, we introduced SnapKV, which maintains constant prompt KV cache counts during generation to reduce serving times. SnapKV selects crucial attention features per head and stores them in a new KV cache, ensuring efficient information retrieval and generation. We also proposed a fine-grained clustering algorithm to retain contextual integrity and improve accuracy in feature selection. In our experiments, we tested SnapKV's performance on models capable of handling extended sequence contexts. We conducted a pressure test on LWM TextChat-1M and an ablation study on Mistral 7B Instruct V0.2 to evaluate the impact of pooling on information retrieval. Additionally, we examined the Command R model and demonstrated that SnapKV can be combined with other acceleration strategies like parallel decoding. One of the tests we conducted, called Needle in a Haystack, evaluated SnapKV's ability to retrieve specific information from lengthy documents. By extending the document length to 380K tokens, we demonstrated SnapKV's capability to manage small details on extremely long input contexts with a significant compression ratio. Section Summary. In this section, we explore the impact of instruction positioning on the interpretability of LLMs and the selection of important features. Our results demonstrate that regardless of whether instructions are placed before or after supplementary contexts, the hit rates remain consistently high, indicating that observation window patterns are unaffected by question positions. Additionally, our investigation reveals that different instructions lead to varying prioritization of attention features, challenging static compression methods and emphasizing the necessity for context-aware compression strategies in LLMs. Section. Decoding speed and memory bound. In this section, we examined the decoding speed and memory usage of the LWM TextChat-1M model with SnapKV under different batch sizes. We set the maximum prompt KV cache size to 2048 for SnapKV. Our experiments revealed two key findings. Firstly, as the input sequence length increases, the decoding speed of the baseline model rises sharply, while the SnapKV optimized model maintains a consistent decoding speed due to the unchanged KV cache. Secondly, the SnapKV enhanced model can decode much longer sequences compared to the baseline model, showcasing an improvement in memory consumption efficiency. We then conducted an ablation study to evaluate the impact of our pooling technique on information consolidation through clustering. By applying max pooling with specific parameters, we observed a significant enhancement in retrieval accuracy compared to methods without pooling. This improvement is attributed to the strong attention mechanisms focusing on the initial tokens, preventing replication of subsequent tokens and leading to more accurate results. Next, we tested SnapKV on 4 models using Long Bench, a benchmark evaluating long context understanding across various tasks. Our results demonstrated that SnapKV effectively captures key information in long contexts and provides detailed summaries with minimal performance drops compared to the original implementations. Additionally, SnapKV outperformed H2O in accuracy on various benchmarks, showcasing its superior performance. Further experiments were conducted on Cohere's Command R model, which showed promising results on tasks requiring long context understanding. SnapKV's impact on retrieval augmented generation (RAG) tasks was evaluated, demonstrating its effectiveness across different benchmarks. By limiting the KV cache size and utilizing specific pooling parameters, SnapKV achieved significant compression ratios without compromising performance. Section Summary. In this section, we benchmark the decoding speed and memory efficiency of SnapKV in comparison to baseline models under different batch sizes. We observe that SnapKV maintains a constant decoding speed as input sequence length increases, resulting in significant speedups and improved memory consumption. Additionally, our ablation study highlights the effectiveness of pooling techniques in enhancing retrieval accuracy, especially in scenarios where strong attention mechanisms are crucial for focusing on key information within long contexts. Section: Needle in a Haystack. In this section, we explored how we can enhance the evaluation of the needle in a haystack task by shuffling context compositions. By permuting context compositions for different lengths and depths, we conducted 8 runs, resulting in more reliable outcomes. We noticed a slight decrease in scores across all models when compared to the original setup without context shuffling. When we applied SnapKV to Command R, even with a 128K sequence length leading to a 32x compression of KV cache, we did not observe any performance degradation. Moving on to retrieval augmented generation (RAG) tasks, which are more complex than synthetic tasks like needle in a haystack and closer to real-world scenarios, we assessed SnapKV's effectiveness. RAG tasks involve selecting relevant documents from a corpus based on a given prompt. Expanding the context window can improve model performance by retrieving more documents, but it also increases memory requirements and latency. SnapKV proved beneficial by reducing memory usage while enhancing performance, especially with sequence lengths up to about 40,000 tokens. In evaluating SnapKV's impact on RAG tasks, we focused on its ability to select relevant documents, crucial for effective RAG. Using an internal benchmark from Cohere, we gathered topic-related documents for each prompt, including ground truth answers and negative samples, totaling 100 documents per prompt. By compressing the KV cache size to 4096, achieving a compression of 5 to 10x, SnapKV retained nearly 98.8% of Command R's performance. Next, we evaluated Command R's generation quality on lost in the middle and generation accuracy metrics. We conducted experiments with different numbers of sample documents and tested SnapKV's robustness by inserting relevant documents at the beginning, middle, and end of the context. SnapKV demonstrated robust generation quality and outperformed the baseline model, especially with close to 200 documents in the context. To comprehensively assess SnapKV's robustness, we integrated it into an end-to-end RAG pipeline. This involved retrieving and re-ranking documents before prompting Command R, resulting in a list of 100 documents for evaluation. SnapKV showcased robust performance in a production-like RAG setting, with a compression ratio of around 4x for an average dataset length of about 16,000 tokens. Lastly, we explored the compatibility of KV cache compression with parallel decoding, aiming to reduce memory overhead in LLMs. By incorporating SnapKV with Medusa, a parallel decoding framework, we improved generation efficiency, particularly in processing long sequences. Empirical results demonstrated a speedup in performance compared to native decoding, highlighting the potential of combining KV cache compression with parallel decoding to enhance LLM efficiency, especially in long context scenarios. Section Summary. In this section, we modified the needle in a haystack evaluation by permuting context compositions to address context influence issues, resulting in more robust results across all models tested. We then evaluated SnapKV's effectiveness in retrieval-augmented generation (RAG) tasks, showcasing its ability to reduce memory usage while enhancing performance, especially in tasks requiring selecting pertinent documents from an indexed corpus. Additionally, we integrated SnapKV into an end-to-end RAG pipeline, demonstrating its robust performance in a production-like setting with a compression ratio of approximately 4x, highlighting its potential in enhancing LLM efficiency, particularly in long context scenarios when combined with parallel decoding frameworks. Section: Discussions. In this section, we discuss SnapKV, which is a powerful yet simple solution that efficiently compresses the KV caches of models to reduce the computational and memory load when dealing with large inputs. We noticed that certain tokens in prompts consistently attract attention from each head during generation, and our approach not only saves important information but also improves processing speed. However, SnapKV mainly focuses on the generative aspect of models by targeting the KV caches, which means it may not help improve a model's ability to handle long contexts or enhance performance if the model struggles with this inherently. Moreover, SnapKV does not address prompt inference processing, which limits its effectiveness when dealing with very long prompts. Nevertheless, our work provides valuable insights and tools for the community, setting the stage for more advanced methods to tackle the challenges of large-scale language modeling.